Hi, my name's Jason Patrick. I'm the Technical Director at ELEK Software. I'm an electrical power engineer with over 20 years of experience. In this free live technical training, I'm going to explain low voltage cable sizing calculations. Initially, I'm going to talk about the low voltage cable sizing standards. I'm going to explain the differences between low voltage and high voltage power cables. I'll give you an overview of active cable sizing and the steps involved. I'll talk about the coordination with protective devices. Also, I'll go through the temperature limits of cable types. I'll give you an overview of derating or correction factors. I'll provide the equation for accurate voltage drop calculations. I will also provide 10 expert tips for accurate voltage drop. I'll explain short circuit ratings, neutral and earth cable sizing, also harmonics and economic or energy efficient cable sizing. Finally, I will go through a fully worked hand calculation example for a 400 volt system with carrying high current over a long length of run. And finally, I'll show you the same example using a new free calculator, cable sizing calculator, which I'll provide the link for at the end of the presentation, which you can use for your own cable sizing calculations. Finally, I'll draw some conclusions and provide some recommendations. And if you have any questions, please add them to the comments on this video. So who is ELEK Software? ELEK Software is a Sydney-based software development company with a focus on power systems design software for cable sizing, low voltage electrical network design, earthing system design in ELEK SafeGrid, and high voltage power cable systems design. We've been developing software since 2009 and we support more than 10,000 users in over 70 countries. Our software complies with multiple international standards. The software I'll be referring to and using within this technical presentation is ELEK Cable Pro web software for low voltage electrical calculations and low voltage network design with switchboards. So for example, that software includes cable sizing to multiple different standards, including the Australian standard, New Zealand, the British standard BS7671, as well as the IEC standards. There is also a maximum demand calculator, voltage rise report, cable pulling calculations, network design with switchboards, including fault level calculations, etc. Protection coordination with more than 10,000 protective devices included in our database, and AC and DC arc flash calculations. Here I've listed out the main low voltage cable sizing standards. When I talk about low voltage systems, I'm talking about cable systems up to 1 kV AC or 1.5 kV DC. So I've listed these standards in no particular order, but there is an IEC 60364-5-52, which is low voltage cable sizing to the international standard, IEC standard. Then there is IEC 60092 for ships. And then there is ASNZS 3008.1. There are two parts of this standard, the Australian part and the New Zealand part. There is BS 7671, which is the British standard. Appendix 4 contains the cable sizing parts for that standard. There is the French standard NFC 15-100. And there is the American standard NEC NFPA 70. So the principles on low voltage cable sizing that I'm talking about today are universal. So the steps and the principles to these calculations apply for all low voltage standards. I won't be talking much about the NEC or American standard during this presentation. but I'll be referring directly to the IEC Australian and the British standards. Alternative specification. So it's important to understand the derivation. Where are these low voltage cable sizing standards derived from, particularly the current capacity tables? Well, those are derived based on IEC 60287, which provides the analytical equations for calculating cable current capacity. This is the fundamental main standard and provides the fundamental equations that are used internationally to derive the current capacity tables in a multitude of these low voltage cable sizing standards, including the Australian standard BS 7671 and the IEC standard 60364. If you look at the notes at the front of these standards, if you search for 60287, you'll find multiple references to the calculations in IEC 60287, that these have been the basis of the tables in these low voltage standards. So that standard IEC 60287 is really quite complicated. There are 9 separate parts to that standard. If you want to do a more accurate calculation, you should use software that's based on this standard. For example, our software, ELEK Cable HV software, is based on that standard, and it can implement or calculate perform cable sizing calculations to your exact specifications, be that your exact cable model and your exact installation conditions. It's not generalized such as the low voltage cable sizing standards are. I've also listed a couple of standards where you can obtain simple lookup tables or current rating tables for medium voltage cables, including the ERA report and the ANSI ICEA report. But again, these tables have all been derived based on IEC 60287. It's the fundamental cable rating calculations standard. So briefly, what's the difference between low voltage cables and high voltage cables? Because the principles are the same, but it's really the constructional differences between these two cable types which causes additional complexity in current rating calculations for high voltage cables. So you can notice in the top right hand corner there's a cross-sectional drawing of photo, I should say, of a high voltage cable, and you'll notice there are actually many different layers to that cable. Insulating layers and metallic layers. There may be metallic screens, metallic sheaths. There may be semiconducting layers over the main conductor, etc. So there can be around 10 different layers to a high voltage power cable. And that's the real difference. In the bottom right-hand corner, you'll see a simple low voltage power cable, 3-core cable with aluminium conductors, but the construction is much simpler. Therefore, these standards for low voltage cable sizing and the current capacity tables have only been based on these simple low voltage cable constructions. Whereas if you need to do a current rating calculation for a high voltage cable, then you'd need to use more advanced software calculations. And you'll need to actually model the cable in the software. So let's talk about active cable sizing for low voltage cables. The minimum active size must satisfy 3 main criteria. That includes current capacity, voltage drop, and short circuit performance. So current capacity ensures that cables do not overheat during operation, and the active cable size is often dictated by current capacity when there's a large load current being carried. Voltage drop, on the other hand, and I apologize for that this slide is a bit messed up, jumbled up. I'm not sure why, but voltage drop prevents excessive reduction in voltage over long distances. So over long route lengths, it's voltage drop that often dictates the active cable size. And then short circuit rating, that's the third main criteria. And that protects cables during fault conditions. Only sometimes, rarely, is the active cable size dictated by the short circuit rating. And that's when the length of run is really quite short and the fault level is relatively high. Then sometimes the active cable size is dictated by the short circuit rating. Additional factors to consider include mechanical strength, the installation conditions, temperature limits of the cable's insulation, which I'll also talk about, and energy efficiency. So here is a high level sort of flow chart explaining all of the steps that you would need to go through to calculate a minimum low voltage cable system conductor size, including collecting data, specifying the length, specifying voltage limits, selecting the protection, selecting the cable type, determining the installation method. That's usually the worst case installation method along the run. Now, if there are multiple installation conditions along the run, then you may need to perform multiple different cable rating calculations and choose the most onerous condition, which results in the largest minimum active cable size. And that's going to dictate the cable that you need to order for an installation. Then the software comes into play. Once you've selected those items, then the software will determine the minimum active size or cable size based on current capacity first. Then it will calculate cable operating temperature, and I'm going to show you all these hand calculations in the example at the end. Next, the software will calculate the minimum cable size based on voltage drop. Now, if that's larger than the size determined at the current capacity stage, then we go back to the first step and we recalculate or we reobtain the minimum cable size, and we recalculate the cable operating temperature. Then again, we recalculate the voltage drops. And then the final step is to determine the minimum cable size based on short circuit performance. And if it so happens that that size is again larger than what was determined during the voltage drop stage, then we have to go back to the start again. So that's what's called an iterative calculation. That's where the software iterates through different options. And if the criteria are not met, the three main criteria that I mentioned are not met, then we step back to the start again and we recalculate. That's why it's really useful to use software for these calculations, because it can be quite tedious and prone to errors if you do these things by hand. It can take you a lot of time. And the beauty also about the software is that the final output is a nice report with all of the results. You can rely on the results. And also with our software includes all of the references to the standards, so you can refer back to the tables that it's used and you can understand how the calculation's being performed. And if you want to verify the calculation, you can do that. So actually there's a minimum cable size for mechanical strength. So at the first step, the first criteria is to determine in the calculation is to determine the minimum cable size to meet current capacity. But we need to start somewhere. We can't start at the minimum cable size that they necessarily manufacture. For power cables, there are requirements set by the standards. For example, the tables here are from the IEC standard in the top right. That's the Australian standard in the top right, and the bottom right is the table from the equivalent standard from the IEC standard, which dictates the minimum cross-sectional area of the conductors. So that's the starting point for current capacity. We cannot use a conductor size smaller than that for mechanical reasons. So look out for that table in your relevant standard. But the software has these tables inbuilt and automatically will not choose a conductor size smaller than that's specified in this table. Coordination with protective device. So we need to coordinate the rating of the protective device with the current capacity of the cable. So looking at this diagram here, starting on the left-hand side, we have the load current IB, which is what it's usually referred to as. And then we have the nominal rating of the protected device, IN, which is the next line moving to the right. So IN is greater than IB. That means that the protective device will not trip, is designed such that it will not trip during maximum load current conditions. And also then moving to the right again, we have the cable current capacity, or the cable current rating, IZ. Now that's on the right-hand side of the nominal rating of the protective device. That means that the protective device rating is selected such that it is less than the current capacity of the cable system, such that the protective device will protect the cable system during an overload condition. Moving to the right, to the far right, we'll talk about the short circuit rating. Also, the short circuit rating of the protected device must be higher than the actual short circuit rating, or the short circuit current of the cable system during a fault. This coordination between the cable system and the protective device is required to avoid damaging the cable system. Temperature limits of cable types. So the temperature limit of a cable dictates the maximum continuous and the short circuit current capacity, or short circuit rating of the cable, and that's predominantly based on the main insulation type temperature limit. So for a PVC insulated cable, the usual continuous maximum temperature limit for that type of insulation is 75 degrees. XLPE is usually 90, and there are also corresponding short circuit temperature limits. So there are different temperature limits during continuous loading, continuous operation, and during a short circuit. Now, it's the continuous, or what's referred to also in the standard as the normal use temperature. That's the temperature that's being assumed for the current capacity calculations. So, and that's the upper limit of the allowable temperature for that cable. And then they perform calculations to determine the current capacity, and that's how they derive those current capacity tables in these low voltage standards. It's based on the normal use operating temperature. Now you'll see from the table in the bottom right hand corner, there's the column for normal use temperatures versus different cable insulation types. And then there's another column to the right of that, maximum permissible temperature or continuous temperature. So that's actually the rating of the insulation type. So in some cases, for example, a V90 insulated cable, the maximum permissible continuous temperature is 90 degrees. But the current capacity tables have been based on a temperature limit, or a 75 degree limit has been used, not the 90 degrees. So it's not that cable type, or that insulation type is not necessarily running at its maximum temperature or even its maximum current. So it's important to be aware what's the normal use continuous operating temperature for your cable type. And this is the table from AS/NZS 3008, which you can refer to. Derating, or they're also referred to as correction factors in the British standard, derating factors are multiplied with the rated continuous current going capacity from the tables of the cable based on standard conditions. So a derating factor of 1 refers to the standard assumed conditions. So the current going capacity tables in these low voltage standards assume an ambient temperature, a depth of burial, and so on. There are a standard set of conditions. Now, if your installation differs from the standard conditions, for example, you're installing cables where the environmental, the continuous or maximum operating temperature of the environment is higher than, for example, the assumed 25 degrees ambient temperature, for example, then you would need to apply a derating factor for ambient temperature. Also, if you are planning to install cables at a deeper burial depth than the assumed standard 0.5 meters of burial depth, you'll need to refer to the derating factor table, select a derating factor, and also apply that to the current capacity of the cable. There are 9 main factors that derate power cables, including ambient temperature, depth of burial, thermal resistivity of the soil, varying loads or load factor, thermal insulation, direct sunlight, which has a very significant impact, harmonic currents, which I'll also be explaining, groups of parallel circuits, which is very common, be that groups on trays or ladders or buried groups, and enclosures. You can see an example where you would definitely need to apply derating factors in the photograph here if we're talking about a low voltage power cable installation. Now, what we do is we select derating factors from the tables in those low voltage cable sizing standards. There are multiple tables for these different factors. We select the derating factor that we need from each of these tables, and we multiply them together, and then we get an overall derating factor, and we multiply that overall derating factor with IZ, which is the current capacity for that cable that we're selecting. Here is the accurate voltage drop equation for low voltage cable sizing calculations. There are lots of different voltage drop equations being used out there in the industry, lots of simple ones. And unfortunately, if you use a simple voltage drop equation, most often you're going to end up with a larger cable size than necessary. Accurate voltage drop equations, such as the one shown here, consider resistance, which is temperature dependent and should be based on the cable operating temperature. The equation should also use cable reactance, which depends on the phase separations of the cables, which in turn affects voltage drop. The accurate equation should also include actual load power factor, which has a significant effect on voltage drop. So you can see the inputs to this equation include load current, the length of run, resistance, reactance, and power factor angle, as well as the number of parallel circuits. We recommend that you always use accurate equations for voltage drop calculations, not simple ones. And of course, with software, our software uses these accurate voltage drop calculations, resulting in lower voltage drop, which in turn results in lower cable sizes or smaller cable sizes. Here's an example of an accurate voltage drop calculation where power factor is having a significant effect. So we're carrying a 3-phase load. The length of run is 200 meters. So more than likely voltage drop is the dictating factor in the cable size. It's a 400 volt supply with a voltage drop limit of 2.5%. We're using a 3-core and earth cable, PVC insulated. So it should be maximum operating temperature or assumed. Normal use continuous operating temperature would be 75 degrees. The conductors are copper. The installation is unenclosed in air and spaced from a surface, which is a standard installation condition. You can see the image in the top right hand corner shown here. Now we've got this table of minimum cable size where let's look at the power factor column. So if we assumed a power factor of 1, the minimum cable size would be 240 square millimeters. Whereas if we assumed a power factor of 0.95, the minimum cable size increases to 300 millimeters squared, resulting in a significant cost increase. Then again, if we had a power factor, if we were carrying a power factor of 0.9, the minimum cable size would need to be increased again to 400 millimeters squared. Now remember, so this shows the importance of considering power factor in your voltage drop calculations. You should remember that the standard rules require users to maintain a power factor of 0.9 lagging or above. Let me provide 10 expert tips for voltage drop calculations. The first one is use accurate equations that consider cable resistance at operating temperature, reactance, and power factor. I've shown you that equation for a 3-phase voltage drop calculation. Remember that for long cable runs, especially to normal loads or relatively small loads, but not necessarily, I'm talking about long cable runs, the cable size is most often dictated by the voltage drop requirements. Sometimes for short runs carrying low load current where the fault current is high, the size may be dictated by the short circuit rating. And I'll actually show you an example of that where the cable size is being dictated by the short circuit rating of the cable coming up in the next slides. Power factor. Power factor can have a significant effect on the minimum cable size, especially for large cable sizes. So if you're carrying large load currents, the assumed power factor is very important, especially for your voltage drop calculation. This is because large cables have a higher reactance than resistance. Therefore, power factor has a big impact on their impedance. Electrical equipment, just remember that electrical equipment that produces poor power factor includes transformers, induction motors, welding machines, and computer equipment. Number 4, heavily loaded cables. Well, the hotter a cable runs or operates, the higher the voltage drop. This is because resistance is temperature dependent, and as temperature goes up, resistance goes up, and so too does voltage drop. Tip number 5 for unbalanced 3-phase circuits. Unbalanced 3-phase circuits produce higher voltage drops. Where out of balance conditions are intermittent or occasional, assume balanced 3-phase load conditions and use the load of the heaviest loaded phase current for your voltage drop calculations. If the out of balance conditions are consistent or permanent, calculate voltage on a single phase basis by summing the voltage drop in the heaviest loaded phase and the neutral. Tip number 6. Multi-core cables have a lower voltage drop in general than single-core cables. This is because single-core cables have a higher reactance. Single-core cables, the separation between the cables is generally higher, resulting in higher cable reactance. Higher cable reactance means a higher voltage drop. But remember that multi-core cables, the same size, conductor size, multi-core versus single-core cable, in general, multi-core cables will have a lower current capacity than their single-core cable equivalent for low voltage power cables. Number 7, flexible cables. Generally, the voltage drop of flexible cables is higher or greater than for non-flexible conductor cables with non-flexible conductors, but can be up to 10% lower for large cable sizes compared to non-flexible cables. This is because the higher number of conductor strands in flexible cables leads to a higher resistance. So they're often much easier to work with, these flexible cables, and they're quite popular these days. However, the standards aren't very clear, especially for aluminium flexible cables. They don't provide accurate resistance values for these cable types. Therefore, you need to obtain resistance values from the manufacturer. The manufacturer may not be willing to provide those values, and so they may be difficult to obtain. We, however, in our software, we've obtained resistance values for flexible conductors, including flexible copper and flexible aluminium cables, and we've included those in our software as options. So therefore, you can get an accurate voltage drop calculation for flexible cables. But remember that voltage drop is usually higher for flexible cables than compared to non-flexible. Tip number 8, motors, dealing with motors. Voltage drop is based on the full load current of the motor. During starting, the terminal voltage should be greater than 80% of the rated voltage. Otherwise, the motor will not or may not start. So we should refer to the nameplate of the motor to obtain the rated current, voltage, and the power factor of the motor from the motor nameplate. This is for voltage drop calculations and current capacity, of course. Here's a tip. For DOL motors, direct online motors, subject to frequent starting and stopping, you should use a multiplying factor of 1.4 times the full load current for your cable sizing calculations. Tip number 9, voltage rise calculations. Voltage rise calculations are exactly the same as voltage drop calculations. There's no difference. For solar applications, there is a voltage rise limit from the inverter to the connection point, so the AC side of the inverter. There is a link on this slide. You can type in that link into your browser. On that web page, there is a bunch of voltage rise limits to particular standards for solar installations. Finally, tip number 10, fire conditions. Critical power and control circuits may need to survive for 30 minutes, 60 minutes, or 120 minutes, depending on their importance and the requirements. It is possible to calculate the voltage drop for cables involved in a fire by assuming the cable temperature in a fire and the cable length affected by the fire. So it's not usually the whole length, but it's a section, and there is a British standard that states that you should generally assume a temperature, I believe it's 834 degrees Celsius for that short duration, and it's a short section of the overall cable length. So you should recalculate the voltage drop and reperform or reevaluate the minimum cable size to survive during a fire. In the absence of performing detailed calculations, you should increase the conductor size by 2 sizes or more for fire. Let's talk about conductors in parallel. The main objective when we're running conductors in parallel is to ensure that there is equal load current sharing between the phase conductors or the multiple conductors in parallel. In order to achieve that, the conductors must be made of the same material, so you must use all copper conductors or all aluminium conductors, and they must have the same cross-sectional area. They must also follow the same route length and have the same length. The parallel cables must be effectively bonded at both ends in the same manner, and the relative position of the active, neutral, and neutral conductors in the circuit and the separation between the circuits must be equal. It should be symmetrical and consistent. As well as a very important point is that the phase arrangement should be optimal. There is a table, an image on the right-hand side of this slide, which describes non-optimized and optimized phase arrangements for multiple parallel circuits. You should follow the optimized configurations in this table for your installation. In the bottom right-hand corner, there is a note to state that the standards dictate that there is a minimum conductor size that you are allowed to run cables in parallel. So in the IEC standard, that's a minimum size of 50 square millimeters for copper conductors or 70 square millimeters for aluminium. And for the Australian standard, it's actually only 4 millimeters squared. So you cannot run parallel conductors for cable sizes less than these sizes dictated in the standards. Short circuit ratings. Remember, I said that that's one of the three main criteria. It always needs to be checked. It rarely dictates the active size, but in the bottom right-hand corner, I've got an example there, a software calculation where the active size is being dictated by the short circuit rating. But really the objective is that the power cables should be able to withstand the short circuit currents for during the short circuit conditions. So the adiabatic equation is used, it's shown here, and that's dependent on the fault current I for the fault clearing time T, and there is a K factor there, which I will explain. The K factor can be either obtained from a lookup table, depending on the standard you're using. So the British standard has a lookup table, the Australian standard and the IEC standard have lookup tables for K factors based on the cable insulation type. But you can also calculate the K factor if you have the maximum temperature, short circuit temperature limit, which I gave on the earlier slides. It's also included in the low voltage cable sizing standards. So you can calculate K, and we recommend that. That's what we do in our software. We think it's more accurate than the simple lookup tables. And you end up calculating an S min, which is the minimum cable size to withstand the short circuit conditions. And like I said, that value is rarely above the minimum size dictated by current capacity or voltage drop. So in the example here, we've got a circuit carrying 20 amps over a short run of 5 meters. And the fault level at the start of that run is 10 kA, so relatively high. So this could be a cable inside or adjacent to a switchboard where the fault level is high and the length is quite short. If you only considered current capacity to carry 20 amperes, I would only need a 1 square millimeter conductor. However, considering short circuit performance, I actually need to, or short circuit rating, I actually need to increase the minimum conductor size to at least 16 millimeters squared. And that's because of the short circuit rating. Neutral cable sizing. It is recommended and in general that The neutral conductor must be at least the same size as the active, and this is quite common, that the neutral is sized the same as the active. However, if there are unbalanced systems, so where there are currents flowing in the neutral, we need to reconsider that. Let's talk about the harmonics, which do cause significant current to flow in the neutral conductor. So for multi-phase circuits, the neutral conductor size can, in theory, be sized smaller than the active size if the harmonic current is less than 15%. This is dictated by the IEC standard. But the other standards, including the Australian standard, don't actually even refer to neutral conductor sizing. I'm talking about the cable sizing standard 3008. It's only AS 3000 which does refer to neutral conductor sizing. But the IEC standard recommends that if harmonic currents are less than 15%, you can in theory reduce the neutral conductor size. And if the neutral current is somewhere between 15 and 33%, I'm talking about the harmonic current traveling the harmonic content of the phase conductors. In that case, the neutral conductor size should be the same size as the active conductor. It's different though when the harmonic current is greater than 33%. And I should also mention that I'm talking about the third harmonics or the triplet harmonics. So for multi-core cables, when you have harmonic currents greater than 33%, the neutral cable size and the active cable size must carry 1.45 times the load current. So in other words, the active cable size is also being dictated by the harmonic component or the harmonic current, and the neutral size the active size is being dictated by the neutral size for multi-core cables. When we talk about single core cables though, when we have harmonic currents of more than 33%, the neutral size must be sized based on 1.45 times the load current of the phase conductor. The active size doesn't need to be increased by this factor. And there is a table shown here that's taken from ASNZS 3008, which provides some guidance for neutral sizing or cable sizing in 4 and 5 core cables when there are harmonics present. I will go into harmonics more after the next couple of slides. Let's talk about earth cable sizing. So there's quite a little bit of misconception about minimum earth cable size. So on the right-hand side of this slide, you'll see a typical lookup table for earth cable size. It provides active cable size in the left-hand column, and then the corresponding minimum earth size corresponding to the active size. So if you're using an active size of 120 square mils, for example, in this table, you look down, and if the active conductor type or conductor material is copper, then I would need to use a minimum earth size of 35 square millimeters. That's using this simple lookup table method. Whereas in fact, the minimum earth cable size needs to be sufficient to ensure appropriate earth fault loop impedance. That means that the protective device must trip during a fault. We need to ensure that. We need to size the earth cable to ensure that. It must also have adequate current capacity to carry the short circuit currents, particularly the earth fault currents for the earth fault clearing time. And we can use the adiabatic equation that I presented earlier for that calculation. It must also have adequate mechanical strength. So the problem with these simple lookup tables, this is the table from ASN AS/NZS 3000. There is also an equivalent table like this in BS 7671. The problem with these lookup tables is they are inaccurate, they're approximate, and they don't ensure appropriate earth fault loop impedance, and they don't ensure appropriate short circuit performance for all cases, not many cases at all actually. We recommend that you calculate minimum earth cable size based on earth fault loop impedance and short circuit performance. And that's what our software does. And in most cases, the minimum earth cable size is actually smaller than what's shown in these simple lookup tables. That's because these tables are conservative. You can choose to follow these tables, but just be aware there are also cases where the calculation produces results or earth cable sizes that are larger than what's given in these tables. So these tables are not accurate very often. Let's talk about harmonic currents and how do we deal with those in cable sizing. So when the active cables are carrying harmonic currents, we can recalculate the active currents by considering or summing the components, including the fundamental current component and all of the harmonic components of the current, to arrive at a new or true RMS IB or load current value. That, in effect, when you're carrying significant harmonic currents, that will in effect increase the active conductor size. And I'll explain the example shown here on the right-hand side very soon. So with high harmonic components in the currents, especially the third harmonics, you will end up with significant neutral currents or currents flowing in the neutral. So for example, on the right-hand side of this slide, you'll see for a three-phase balanced 100 amp system, so the currents in the three phases are perfectly balanced. That's for the fundamental frequency, 50 hertz, for example. As we add third harmonics, so starting at 10%, you'll see in the top left-hand corner plot, phase plot, you'll see the red and the blue. So the red is the current, the phase current, and you'll see that starts to become distorted when we're carrying 10% third harmonics in the phase currents. And then the top right-hand plot, the neutral current, the red curve in the top right-hand plot, displays the neutral current. Currents start to flow in the neutral. And we can see the values in the top right. At 10% third harmonics, we've got a true RMS phase current now increased to 100.5 amps. So not much of an increase, but we still need to consider that current, that true RMS current for our current capacity and our voltage drop calculations. But now we've got more than 28 amperes running or flowing in the neutral. As we increase the third harmonic current, so components, so we go to 20% third harmonics, 30%, etc. Both the true RMS current in the phase conductors increases. So not by too much, so 100.5, 101.98, 104.4, and finally with 50% third harmonics, 111.8 amperes. That's the true RMS current in the phase conductors when there are 50% third harmonics. But at 50% third harmonics, the neutral current is higher than the phase current at 143.35. And that's the condition where the IEC mandates that the neutral cable size actually needs to be larger than the active cable size in this case. And you can see the reason why. It's carrying a higher load current than the phase conductors. So performing these harmonic calculations is you need to enter harmonic profiles for different loads, and then you can sum the currents in the active cables and also the neutral. These calculations are a little bit tricky, a little bit involved. You need to use software for that. To do that calculation, you should perform a low voltage network calculation involving all of the loads and all of the system, including the switchboards, and you should sum the currents including the harmonics at each of the switchboards as provided by the loads, etc., and especially at the main switchboard. And you should size your cables based on uh, all of the fundamental frequency currents and the harmonic currents. You can do that using our software, ELEK Cable Pro Web, our LV network calculator. Let me talk about economic or energy efficient cable sizing. So the principle of this cable sizing method is to select a cable size where the cost of the losses over the lifetime is minimized. So we've talked about a method to size your low voltage power cables based on those three main criteria: current going capacity, voltage drop, and short circuit rating. So that's what we could say is the minimum safe size. But if we consider the lifetime of the cable, now remember, when these cables operate, is electrical heating caused by the current flow. There are I squared R losses. Now, over a long time, those losses, because they don't do any real work other than produce wasted heat, those losses result in an economic loss to the owner over the lifetime of the cable. Now, what if we considered those losses over the lifetime during our cable sizing design period? Now, it's the fact that a larger cable size, because it has lower resistance, will have lower losses over time. So a larger cable size will have a higher initial cost, but over the lifetime, the losses will be lower. So the cost of the losses, or the cost of the ownership, will be lower. So that's the principle of this economic cable sizing. It's an optional method. There is a method outlined in AS/NZS 3008, which we think is quite good. We have implemented this method, and there is an example shown on this slide of the end result. But there are a couple of problems with this method, in that the first problem for the designer is that you need to know or assume some extra information. So you need to know the cost of your cables for different sizes. You need to know, ideally, not just the cost of the cable, but if you were to use a larger cable size, what could be the extra installation costs for installing a larger cable size. So that's about the initial conditions. Then you also need to know values such as the discount rate, which is like an assumed interest rate, and the cost of electricity, because we need to calculate the cost of the electrical losses over the lifetime. And you'll need to know what's the lifetime of the cable installation. Then you can perform an economic cable sizing calculation. In this example, so it demonstrates the process. So we start with the minimum cable size result based on the current capacity, voltage drop, and short circuit rating. That's the safe minimum size. Then we perform the economic cable sizing calculation with the discount rate and the cost of electricity. And we have arrived in this example at quite a significant larger cable size, an optimal economic size of 240 millimeters squared. There is an optimal size, and you can determine that using this calculation, and that results in an overall cost savings over the lifetime of the cable system of almost $10,000, with a payback period of almost 4 years. Another major drawback with the implementation of this method, of course, is convincing your client, your customer, that it's a good thing to do, and that over time it will save them money. I guess when you're submitting quotes, if you to remain competitive, if you were to submit the economic cable size, you wouldn't be necessarily competitive. So it's avoided quite often in the industry at this time. But I think for owner operators, it's definitely a no-brainer and makes a lot of sense. So right now I'm going to show you a fully worked hand calculation for a cable sizing calculation. It's for a long cable run carrying a high load current. I'll step you through all of the hand calculations with the equations, and then I will show you how to do the same calculation using a ELEK cable sizing calculator. Right now, I'd like to share with you our free cable sizing calculators. If you go to the web address elek.com/calculators, you'll see that we are providing multiple free professional cable sizing calculators to multiple standards, including the Australian standard, New Zealand standard, British standard BS7671, and coming very soon, in a matter of weeks, is the IEC cable sizing calculator. You'll see other calculators, free design calculators that you can use there as well. These are fully functioning professional calculators which you can use for your design calculations. Here is an overview of the worked example I'm going to show you. It's a three-phase circuit with a current carrying a current of 1200 amperes. The length of the circuit is 260 meters. It's a 400 kV, 400 volt supply with a voltage drop limit of 3.2%. The cable type is 3-core and earth, XLP insulated, copper conductors. The insulated is buried in separate conduits. And the fault level is 15 kA for 1 second. Right now, I'm going to show you how to perform those cable sizing calculations by hand. Then I'm going to show you using the free cable sizing calculator. So let me go through this worked example of a three-phase 400 volt system where we're performing the cable sizing calculation for a high load current over a long run. I've already explained the input parameters. First step is to determine the minimum size to meet current going capacity, so it's 1200 amps. We need to select the correct or appropriate current going capacity table from this standard. In this case, we are using AES-NZS 3008.1, the Australian standard. Now we are using XLP insulated cables, three-phase system, and the installation condition is installed in separate conduits. So that's table 8, column 27. The conductors type is copper. Now we need to provide a cable size that allows up to or more than 1200 amperes. So we can see from this column, second last column on the right, versus conductor size, up to a maximum conductor size of 630 square mil, we can see that the maximum current for a single circuit of 630 square mil does not meet 1200 amps, only provides 820 amps. So therefore we need two circuits of some other size. We are proposing that should be two circuits of 400 millimeters squared cable. So the current going capacity of a single 400 millimeters squared circuit in this case is 626 amps. multiply by 2, and we arrive at 1252 amps, which is the current capacity of 2 sets of 400 millimeters squared cables, which exceeds our requirement of 1200 amps. So that meets current capacity. Let's move on to the voltage drop requirements. There is a maximum allowed voltage drop of 3.2% over a run of 260 meters. It's a little bit difficult to know offhand what would be the optimal or the required minimum cable size to meet that voltage drop requirement. So I'm making it easy in this case and proposing, because I already knew the answer, so I'm proposing 3 sets of 630 square mil. But in reality, you would need to try different sizes until you arrive at the size that also meets the voltage drop requirements. Now, to do that, to do it by hand, maybe you'll use a simple voltage drop equation until you have a ballpark figure, and then you'll use the accurate equation to get the accurate voltage drop. But it really is much, much easier and faster and more accurate to use software, but I'm showing you how to do it by hand. So 3 sets of 630 square mil cable to meet voltage drop requirement. First thing we need to do to get an accurate voltage drop value is to equate the cable or determine the cable operating temperature using this equation here. We need to rearrange for theta r, which is the third variable down. For that, we need to input these variables. 1200 amps, that will be the operating current. The rated temperature, 90 degrees for XLPE cable. That would be the normal use operating temperature. The ambient temperature of the soil, 25 degrees in the case of this standard. And we also need to enter the rated current of the circuit, which for these 3 sets of 630 square mil, which is 2,460 amps. And it turns out when we calculate cable operating temperature, the result is a little over 40 degrees Celsius, so up from 25 degrees. So that means that when these 3 sets of 630 square mil cable are carrying only 1200 amps, so less than 50% of their capacity, then they will operate at 40 degrees Celsius. The cables will operate at 40 degrees. Now, we use that cable operating temperature to determine the cable resistance. So there are tables for cable resistance in the standards. In this case, it's table 34. Now, we're using single core cables, so this is the table for single core cables. And we have conductor size in the left-hand column, and we have conductor type or conductor material, copper and aluminium. So copper is from columns 2 to 7 versus conductor temperature along in the columns as well. Now for our conductor size, the minimum temperature they have in this table is 45 degrees. For the conductor temperature, it is conservative to assume a higher operating temperature than the actual. So the actual is just less than 41 degrees Celsius. We are using a resistance at 45 degrees, which is slightly conservative. But you'll notice along the columns, as you increase temperature, resistance does increase. But it's more accurate and it gives a better result for us. It results in slightly smaller, well, sometimes significantly smaller cable sizes if we assume the resistance at operating temperature for our voltage drop calculation. So we have our resistance value. Those units are in ohms per kilometer. We'll use that in our equation. There's a different table for cable resistance. Table 30 in this case, based on single core cables and the insulation type and the arrangement. We are arranging the cables in trefoil versus conductor size. We have our reactance, cable reactance value. So the resistance and the reactance, the operating current and the length are all used for our accurate voltage drop calculation. We arrive at a three-phase voltage drop of 12.49 volts. We convert that to percentage by dividing that by 400 volts to get 3.12%, which meets our requirement maximum voltage drop limit of 3.2%. Therefore, three parallel sets of 630 mil cable is appropriate to meet current going capacity and voltage drop. Finally, we do need to calculate short circuit rating. I don't think that it's going to be an issue. For that calculation, we can also use our resistance and reactance values to calculate an impedance of the cable circuit. We know the prospective fault current at the supply end of the circuit that was 15,000 amps. Using the impedance of the circuit, that is reduced to 7,829 amps at the end of the circuit. We will use that for our short circuit sizing or short circuit rating of the cables. We'll use this I squared T equals K squared times S squared. We rearrange that for S min, which was provided in the slides. We know I, we know T. We also, we can either use a lookup table for K, or we can calculate it. In this case, we know the maximum conductor temperature during short circuits is limited to 250 degrees for XLP insulated cables. We get our K value from this table here, table 52. We've got copper conductor. There's the maximum final temperature, or referred to as the final temperature for short circuit. And we must match that with the initial conductor temperature, remember 45 degrees. So 168 is our K value. And we use the K value to get an S min, which is 46.61 millimeters squared. So to meet short circuit rating or short circuit capacity, we must have a cable size greater than 46 millimeters squared. We certainly do. We are using 3 runs of 630 square mil cables, so short circuit rating is not an issue. Nonetheless, it needs to be checked. Let's look at neutral cable sizing. In this case, we are just using the neutral size to be the same size as the active conductor to meet the Australian standard 3000. And then earth cable sizing, remember I said you can either use this simple lookup table, table 5.1 from AS3000, there is an equivalent in BS7671, or otherwise you can calculate it based on the short circuit rating and the fault loop impedance, which is recommended. I'm not going into details into that calculation here. It's much easier to do in the software, which automatically performs all the checks, and I'm going to show you that next. So here are the free cable sizing calculators that I mentioned. If you go to elek.com/calculators, you can use these cable sizing calculators for free. We have multiple standards. In this case, I'm going to open the Australian standard cable sizing calculator. So this is a fully functioning professional cable sizing calculator. So it has different sections. We've got the load, supply, cable, installation, and then the cable sizing results are updated live on the right-hand side. In the bottom right-hand corner, we've also got our protection system where we can select multiple different types of protection systems as required. So starting in the top left-hand corner from the load inputs, so it was 1200 amps was the supply. Derating factors, there is a derating wizard where you can select from all of the derating factor tables in the standard. Power factor, I didn't actually mention it, but it should be 0.9 in this example. Let's select a 3-phase system. The voltage drop requirement is 3.2%. That's a 400 volt system. The length of run, 260 meters. The fault level, 15 kA. The cable insulation, XLP insulated. copper conductors, single core cables, the installation condition, buried enclosure in separate ducts, and there's the result on the right hand side. You've got 630 square mils, 3 circuits. We've got neutral size, earth size, voltage drop 3.14%, fault loop impedance, automatic conduit sizing. We also have detailed results in this tab here for the current capacity, including the table that's being used, table 8, column 27, cable operating temperature, voltage drop, conductor impedance, short circuit performance, and fault loop impedance. As I mentioned, you can freely access these cable sizing calculators. There is a report generation function, and you can use these for your own calculations. Thank you. Finally, let me draw some conclusions and recommendations. The key areas of low voltage cable sizing calculations includes current capacity calculations or lookup tables, derating factor selection. Those are provided in multiple tables in the standards. Remember, I talked about the 9 main factors that derate a power cable. Voltage drop requirements and calculations, short circuit performance, neutral and earth cable sizing, additional considerations including Harmonics calculations, economic and energy efficient cable sizing calculations. Let me provide some recommendations from myself. First thing is to calculate cable sizing using an electrical network calculator. That's a more accurate method than doing cable sizing calculations in isolation. It's better to model your electrical network, including switchboards, to calculate any unbalanced conditions and to meet your overall network voltage drop requirements, etc. Secondly, you should use accurate voltage drop calculations and equations. Thirdly, calculate minimum earth cable size rather than use simple lookup tables. And finally, utilize derating factors from different standards. Sometimes that can be quite useful, quite handy, but consider the differences in the assumed standard conditions. Thank you for watching this free training on low voltage cable sizing calculations. Don't forget to try our free cable sizing calculators at elek.com/calculators. I'll see you again on our next training session. Thank you.